In 1738, French scientists fired cannons across the hills of Paris and clocked sound racing at roughly 337 meters per second. But this triumph was built on a century of failure. Marin Mersenne's 1630s estimate missed by nearly 15%, and Newton's own 1687 calculation was embarrassingly too slow. Each echo, flash, and gunshot inched humanity closer to a number nobody could see. So why did Newton, the greatest mind of his age, get the speed of sound so badly wrong? To answer that, we have to go back to a time when nobody believed sound had a speed at all. For most of human history, sound simply arrived. You spoke, and the person beside you heard you. There was no gap, no delay, nothing to measure. Aristotle, working in the 4th century before Christ, treated sound as something that traveled through air, a disturbance passing from one place to another. But how fast? That question barely occurred to anyone because the everyday world offered no reason to ask it, and yet the sky itself kept dropping a clue. Anyone who watched a storm noticed the strange lag. Lightning flashed, and only seconds later did the thunder roll in. The two clearly came from the same event, so why did one arrive late? The honest answer was that sound took time to cross the distance. That single observation should have cracked the problem open. Instead, it sat unused for centuries because there was a wall no thinker could climb. That wall was time itself, or rather the inability to measure small slices of it. The delay between lightning and thunder was only a few seconds, and no clock in the ancient or medieval world could carve seconds into reliable pieces. You cannot measure a speed if you cannot measure the moments it fills. So the finite speed of sound remained a suspicion, a thing felt in the belly during a thunderstorm but never pinned to a figure. Pinning it down would take a man willing to treat sound like a runner on a track, and that man was Marin Mersenne. Working in the 1630s, this French friar and mathematician decided to stop philosophizing and start timing. Born in 1588 in the village of Oisey and educated by the Jesuits at La Flèche alongside the young René Descartes, Mersenne ran a correspondence network that linked more than 140 scholars across Europe, effectively acting as a one-man scientific journal decades before such journals existed. His tool was the echo. He would make a sharp sound, then wait for it to bounce off a distant wall and return to his ears. If he knew the distance to the wall and the time the round trip took, he had everything he needed. The distance was the easy part. He could pace it out and measure it. The time was the nightmare. Mersenne had no stopwatch, so he leaned on his own pulse and on the steady counting a trained ear could manage. From these crude beats he arrived, in 1636, at a speed near 450 meters per second, a result he published in his sprawling treatise Harmonie Universelle that same year. By modern standards, that number is far too high, off by roughly 15%, roughly 113 meters per second above the truth. But that is not the point. The point is that a human being had finally attached a number to sound at all. Mersenne's high figure begged for a cleaner signal, and Pierre Gassendi thought he had one. A priest, astronomer, and rival of Descartes, who would later hold the chair of mathematics at the College Royal in Paris from 1645, Gassendi brought a sharp observational instinct to the problem. Around the same years, between 1635 and 1640, Gassendi realized that a gunshot gave you two events in one, the flash of the powder and the bang that followed. The flash, he reasoned, was effectively instant. The bang lagged behind. Time the gap, and you time the sound. This was a genuine leap because it separated the trigger from the arrival with something far crisper than an echo. Gassendi's measurements landed around 478 meters per second, still too fast, but arrived at through a smarter method. Where he went wrong was in his reasoning about pitch. He assumed that a high note and a low note traveled at different speeds, that the sound itself carried its own tempo. That assumption was simply false, and it would haunt the work of others until someone thought to test it directly. Testing it directly is exactly what a group of Italians set out to do. In 1657, in Florence, a remarkable club of experimenters came together as the Accademia del Cimento. Founded under the patronage of Grand Duke Ferdinando II de' Medici and his brother Prince Leopoldo, The Academy gathered around 10 members, among them Giovanni Alfonso Borelli and Vincenzo Viviani, the last surviving pupil of Galileo. Their name meant the Academy of Experiment, and they lived up to it. Their motto, Provando e Riprovando, meaning testing and testing again, captured a philosophy that would outlast their brief 10-year existence before political and religious pressure dissolved them in 1667. They distrusted assumptions and demanded that nature answer under controlled conditions. Sound was one of their targets, and cannon fire was their instrument. They timed the flash and boom of artillery across measured distances, and their number came in dramatically lower than anything before, around 350 meters per second. This was the first estimate to hover near the truth. But their greater gift was what they proved about pitch. By listening carefully to high and low notes fired across the same stretch, they confirmed that every note arrived together. A booming bass and a shrill treble crossed the field at the same speed. Gassendi's old assumption was dead, though its ghost lingered for decades. With the experimenters closing in, a very different kind of mind decided to attack the problem from the opposite direction. Isaac Newton did not want to fire cannons. He wanted to derive the speed of sound from pure principle, from the very laws of matter and motion he had laid out. In his Principia of 1687, specifically in the second book, Proposition 49, he treated sound as a pressure wave squeezing through air and worked out how fast such a wave should ripple. It was a breathtaking ambition, and it produced a number, about 298 meters per second. The trouble was that this figure sat roughly 15% below the true value. Newton, the man who had chained the planets to mathematics, had come up short on something as ordinary as a shout across a field. He knew it was too low. He tried various fixes and fudges to nudge the number upward, invoking the physical bulk of air particles and the presence of water vapor to conjure an extra fifth or so of speed, but none of them were honest physics. The gap between his theory and the world's canons was real, and it would sit unsolved for well over a century. While theory stalled, measurement pressed on, and it found a patient champion in an English clergyman. William Durham, a Fellow of the Royal Society and Rector of Upminster in Essex, took to the countryside between 1704 and 1708 with guns, a telescope, and a pendulum. Working often from the tower of his Church of St. Lawrence, he sighted landmarks up to 12 or 13 miles away, including church spires he could name across the flat Essex plain. His setup was the most careful yet assembled. He would watch through the telescope for the flash of a distant gun, then count the swings of a pendulum until the bang reached him. That pendulum was the quiet hero of his work, because it gave him a repeatable, trustworthy unit of time, something Mersenne could only dream of. Across his fields, Durham measured sound at about 348 meters per second, a figure that has aged remarkably well and which he published in the Philosophical Transactions in 1708. But his sharpest insight was not the number. It was his observation that wind and weather shifted his results. Fire with the wind and the sound came faster. Fire on a cold day and something changed. He had brushed against the true hidden variable, though he could not yet name it. Naming it required canceling out the very wind Durham had noticed, and the French set about doing exactly that. In 1738, near Paris, a grand experiment was staged with military precision under the authority of the Académie des Sciences, with figures such as Cassini de Thury involved in the survey work. Cannons were placed at 2 distant stations, and each fired toward the other. This was the clever part. If wind sped the sound one way, it would slow the sound the other way by the same amount. Average the 2 trips, and the wind simply erased itself. The averaged result came out near 337 meters per second, and crucially, they understood it applied to still, cold air at around 0 degrees Celsius. This was the cannon experiment that opened our story, the triumph on the Paris hills. It was accurate, it was rigorous, and it was the culmination of 100 years of firing guns and counting beats. Yet even this proud number carried an asterisk, because the scientists still could not fully explain why different days and different measurements had disagreed for so long. The explanation had been hiding in Durham's weather notes all along. It was not pitch that changed the speed of sound, as Gassendi had wrongly guessed. It was temperature. Sound moves faster through warm air than through cold, and the effect is surprisingly regular. The speed rises by about 0.6 meters per second for every single degree Celsius you add. Heat up the air, and its molecules jostle more eagerly, passing the pressure wave along a little quicker. Once you grasp this, the whole messy history snaps into focus. The wildly scattered estimates of earlier experimenters were not all sloppy work. Some of them were simply measuring on different days, in different air. A summer measurement and a winter measurement should disagree, and now everyone knew why. Temperature was the invisible hand that had been nudging every result, and pinning down the speed of sound now meant pinning down the thermometer beside the cannon. But temperature explained the scatter between experiments. It did not explain Newton's stubborn error. His theory was too slow, no matter the weather. That embarrassment finally fell to Pierre-Simon Laplace, who cracked it around 1816. Laplace saw what Newton had missed about the physics of the wave itself. When sound passes through air, it compresses each little pocket of gas and then releases it, over and over, incredibly fast. Newton had assumed those compressions happened slowly enough for heat to leak away and even out. Laplace realized the truth was the opposite. The squeezing happens so quickly that heat has no time to escape. Each compressed pocket briefly warms, and that extra warmth stiffens the air and speeds the wave. Laplace added this correction, known today as the adiabatic factor, tied to the ratio of the specific heats of the gas, a value close to 1.4 for ordinary air. Taking the square root of that ratio supplied almost exactly the missing 18% Newton had chased in vain. When he plugged it in, his prediction jumped to about 340 meters per second, landing squarely on the experimental value. That single correction was a moment of quiet glory. Theory and experiment, at war since 1687, finally shook hands. Newton had not been foolish. He had simply left the heat in the wrong place. Laplace put it where it belonged, and the number that cannons had chased for 100 years now fell out of pure mathematics. Acoustics had become a subject where you could calculate the answer and trust the field to agree. And once the air was understood, a natural question surged forward. If sound needs a medium and warm air carries it faster than cold, what happens in a medium far denser than any air? What happens underwater or inside solid metal? The answer would humble everyone who thought of sound as a slow, lazy traveler. The water question was settled on a lake. In 1826, on Lake Geneva, Jean-Daniel Colladon and Charles Sturm ran one of the most elegant experiments in the history of science. Colladon, a Swiss physicist then in his 20s, and Sturm, a mathematician of German origin, stationed their boats some 13,487 meters apart between Roll and Thonon. In one boat, they struck an underwater bell and at the same instant flashed a light. In a distant boat, an observer watched for the flash and listened, through a submerged tube, for the ringing that followed. Once again, it was flash against sound, the same trick as the old cannons, but now with the lake itself as the racetrack. Their result was stunning. Sound tore through the water at about 1,435 meters per second, more than 4 times faster than through air. Density and stiffness, it turned out, hurried the wave along rather than dragging it back. And the trend did not stop at water. In steel, sound races beyond 5,000 meters per second, over a mile every second, streaking through the metal faster than any cannon on any Paris hill. The medium, not the sound, wrote the speed. With air, water, and solids all accounted for, the long hunt could finally settle on firm ground. The accepted modern value for sound in dry air lands at 343 meters per second at 20 degrees Celsius and at 331 meters per second when the air chills to 0. Look at those figures beside the old cannon results and something remarkable stares back at you. The Academia del Cemento's 350, Durham's 348, the French Academy's 337, all of them were clustered around the truth that precise 19th and 20th century acoustics finally confirmed. Those men, counting pulses and pendulum swings across muddy fields, had been circling the right answer with nothing but powder, patience, and a good ear. The modern number did not overturn them. It vindicated them. Step back and the arc is astonishing. From Mersenne's rough 1636 estimate to Laplace's 1816 correction runs, nearly 180 years of steady refinement. Generation after generation inherited a slightly better number and handed on a slightly better one. No single genius solved the speed of sound. A relay of careful minds did, each fixing an error the last had left behind. And what they built was not a trivia answer. It was a method, a way of turning a whisper into a measurement, a way of trusting experiment over assumption. That foundation runs straight into the modern world. Sonar that maps the ocean floor depends on knowing how fast sound crosses water. Aviation lives and dies by the speed of sound in air, the barrier every fast aircraft must reckon with. The whole science of acoustics rests on those flashes and bangs. Sounds speed one was, one bye hef, whos. It was won by friars counting their pulses, by Italians firing cannons, by a clergyman in a field, and by a Frenchman who finally put the heat back where it belonged. What began as a shrug at thunder became a number you can trust with your life. If this journey through sound and fire moved you, consider subscribing so you can join the next story we chase.